Welcome to this problem walkthrough. Today, we'll explore LeetCode problem number 1995, count special quadruplets. In this problem, we aim to find quadruplets that satisfy specific conditions. We'll break the problem into digestible steps, analyze the approaches, and discuss their trade-offs. Let's dive in. In this problem, we are tasked with counting something called special quadruplets from a given integer array nums. The array is zero-indexed and has a length n. A quadruplet is a group of four indices, A, B, C, D, that satisfies two key conditions. First, the indices must follow the strict order 0 equals A less than B less than C less than D less than n, meaning they are strictly increasing and within the bounds of the array. Second, the sum of the elements at indices A, B, and C must equal the value of the element at index D. Our goal is to compute the total number of such quadruplets that meet these criteria. The input to this problem is the array nums, which has a length constraint of 1 to 50, and each element in the array is between 1 and 100. The output will be an integer representing the count of these special quadruplets. To better understand the problem, let's look at an example. Suppose the input array nums is 1, 2, 3, 6. The output for this case is 1. Why? Because there is exactly one special quadruplet, 0, 1, 2, 3. If we calculate the sum of nums 0, nums 1, and nums 2, we get 1 plus 2 plus 3 equals 6, which is equal to nums 3. Therefore, this quadruplet satisfies the conditions. Now, consider another example where the input array is 1, 1, 1, 3, 5. In this case, the output is 0 because there are no quadruplets in the array that satisfy the condition nums A plus nums B plus nums C equals nums D. Let's look at a third example to explore a more complex scenario. If the input array is 1, 1, 1, 1, 1, the output is 5. Here, there are 5 special quadruplets that meet the conditions. For instance, the quadruplet 0, 1, 2, 3 works because the sum of nums 0, nums 1, and nums 2 equals 3, which is the value of nums 3. Similarly, 0, 1, 2, 4 is valid because the same sum of 3 equals nums 4. Another example is 0, 1, 3, 4, where nums 0 plus nums 1 plus nums 3 equals 3, which matches nums 4. These examples show how multiple quadruplets can coexist in arrays with repeated values. The remaining two quadruplets in this example are 0, 2, 3, 4, and 1, 2, 3, 4. Both follow the rule that the sum of nums A, nums B, and nums C equals nums D. Now, let's consider the constraints and edge cases you may encounter. The array length n is at most 50, so while the problem allows up to n-4 quadruplets in the worst case, such brute force solutions are computationally expensive for larger values of n. Efficient approaches are required to optimize the solution. Edge cases include arrays of minimum length, such as n equals 1 or n equals 4, where there may be no quadruplets at all. Additionally, arrays with all elements equal or arrays where no quadruplets exist present unique challenges. These constraints and edge cases highlight the need for careful algorithm design to solve the problem effectively. To solve this problem, we first consider the brute force approach. The intuition here is straightforward, since we are looking for quadruplets A, B, C, D that satisfy specific conditions. We can try all possible combinations of indices where A, B, C, and D follow the order 0 equals A less than B less than C less than D less than n. For each combination, we simply check if the sum of the first three numbers, nums A plus nums B plus nums C equals nums D. The algorithm involves using 4 nested loops to iterate through all possible indices, and for every valid combination, we increment a counter whenever the condition is met. While this approach is intuitive, it has a time complexity of n to the power of 4, as we are iterating through 4 nested loops. This makes it computationally expensive for larger arrays, such as when n equals 100, because the number of combinations grows exponentially. Additionally, the space complexity is 1, as no extra space is used beyond basic variables. However, due to its inefficiency, this method is impractical for larger inputs. Now, we can explore an optimized approach using hashing. The key observation here is that we can reduce redundant computations by pre-computing and storing certain sums. Specifically, instead of recalculating sums repeatedly, we can use a hash table to store and quickly retrieve the values needed. The algorithm works by iterating through the array in reverse order to fix the index d. For each d, we store the value of nums, d, in a hash table. Then, for every combination of indices a, b, and c where a less than b less than c less than d, we calculate the sum nums, a, plus nums, b, plus nums, c, and check if this sum exists in the hash table. If it does, we count that quadruplet is valid. This approach reduces the time complexity to O(n) cubed, as the hash table lookup is efficient and eliminates the need for an additional nested loop. The space complexity is O(n), because we only store the values of nums, d, in the hash table. While this method is significantly faster than the brute force approach, it can still be computationally expensive for very large input sizes. Another optimized approach involves pre-computing sums to further improve efficiency. Here, instead of fixing d and iterating through all possible combinations of a, b, and c, we pre-compute all possible sums of two numbers and store these in a hash table. For every pair of indices, I, j, or I less than j, we calculate the sum nums, I, plus nums, j, and store it in the hash table along with the corresponding indices. Then, we iterate through all possible pairs, c, d, or c less than d and calculate the difference nums, d, nums, c. If this difference exists in the hash table, it means there is a valid quadruplet, and we increment the counter. This approach reduces the time complexity to O(n) squared, as we only iterate through pairs of indices. However, the space complexity increases to O(n) squared, due to the storage of all pre-computed sums, which can be prohibitive for very large input sizes. While this method is faster than the hashing approach, the trade-off in space requirements makes it less practical for large arrays. In this problem, we selected the optimized approach using hashing as the chosen strategy. This approach strikes the right balance between time and space complexity, making it both efficient and practical for moderate input sizes. Although the pre-computed sums approach is faster with its O(n) squared time complexity, its space complexity of O(n) squared can become infeasible for large inputs. The hashing approach, on the other hand, uses a hash table to efficiently check for valid quadruplets while maintaining a manageable space complexity of O(n). The key insight here is that the problem revolves around finding subsets of indices that satisfy a specific sum condition, which can be optimized using hash tables. By iterating in reverse order and fixing d, we naturally ensure that the condition a less than b less than c less than d is satisfied without requiring additional checks. In terms of trade-offs, the brute force approach, while simple, is too computationally expensive. The hashing approach offers a balanced solution, while the pre-computed sums approach sacrifices space for time. Overall, the hashing strategy provides a robust and scalable solution for this problem. In this problem, we are tasked with finding all unique quadruplets in an array nums that satisfy two key conditions. First, the indices of the quadruplet must follow the strict order 0 equals a less than b less than c less than d less than n. Second, the sum of the elements at the first three indices must equal the element at the fourth index, meaning nums, a, plus nums, b, plus nums, c, equals nums, d. To solve this, we can start with a brute force approach. This method, while straightforward, involves systematically checking all possible quadruplets. The first step is to iterate through all combinations of indices using 4 nested loops. Each loop will ensure that the indices follow the required order. Once we have a combination of indices, we calculate the sum of the elements at a, b, and c. Finally, we check if this sum equals the element at d. If the condition is satisfied, we store the quadruplet in our result list. This algorithm ensures that no potential quadruplet is missed, but it comes at the cost of efficiency, especially for larger arrays. The next step in the brute force approach is to output the final result. After iterating through all combinations, we return the collected list of quadruplets that satisfy the required condition. Here's a simplified pseudocode representation of the algorithm. We initialize an empty list to store our results and iterate through all possible combinations of indices using 4 nested loops. For each combination, we check if the sum of the first 3 elements equals the fourth. If it does, we append the quadruplet to our result list. Finally, we return the result. However, it's important to recognize the limitations of this approach. The time complexity is a significant concern, as the algorithm involves 4 nested loops, each iterating over the array of size n. This results in a time complexity of O, n to the power of 4. While the space complexity remains O, 1, aside from the result list, the sheer number of iterations makes this approach infeasible for large input sizes. The brute force algorithm has clear scalability issues. With a time complexity of O, n to the power of 4, the number of combinations grows exponentially as the size of the input increases. For example, when n is 100, there are nearly 3.9 million combinations to evaluate, which can make the program extremely slow. Another drawback is the presence of redundant calculations. The same sums are computed repeatedly for different combinations of indices, leading to inefficiencies. Additionally, it's important to consider edge cases. If the array has fewer than 4 elements, it's impossible to form a quadruplet. For arrays with identical elements, the algorithm still needs to handle them correctly, such as in the case of 1, 1, 1, 1. Arrays with negative numbers or zeros are also valid inputs since addition works naturally with these values. To address these inefficiencies, we can explore optimizations like hashing or the two-pointer technique, which significantly reduce the number of computations required. One effective optimization involves using a hash map to store sums of pairs of indices. Instead of iterating over all possible values of d, this method allows us to quickly look up whether a corresponding sum exists, which drastically reduces the time complexity. Another optimization is the two-pointer technique. After fixing two indices, we can use two pointers to find pairs of indices that satisfy the condition, eliminating the need for some nested loops. Pre-sorting the array can further simplify the two-pointer approach, as it allows for more efficient traversal. However, sorting introduces an O, n log n, pre-processing step, which is still far more efficient than the brute force approach for larger arrays. To better understand the flow, let's consider an example. Given nums equals 1, 2, 3, 6, we start by fixing indices a equals 0, b equals 1, c equals 2, and d equals 3. The sum of nums a, nums b, and nums c is 1 plus 2 plus 3 equals 6, which matches nums d. This valid quadruplet, 0, 1, 2, 3, is added to the result. The output for this input is a single quadruplet, 0, 1, 2, 3. The brute force approach utilizes simple data structures to solve the problem. The input array, nums, allows for random access to elements, which is necessary for direct indexing. The result list is used to store the quadruplets that meet the condition, making it easy to return the final output. However, while conceptually straightforward, this method is not practical for larger input sizes due to its inefficiency. Optimized techniques, such as using a hash map for faster lookups or employing the two-pointer method, are better suited for real-world applications. These approaches not only reduce the computational overhead but also make the algorithm scalable to larger inputs. While the brute force method serves as a good starting point to understand the problem, applying these optimizations ensures that the solution remains efficient and practical for a wide range of scenarios. The provided Python implementation solves the problem using a brute force approach. The goal is to count all quadruplets, A, B, C, D, such that the sum of three elements equals the fourth and the indices satisfy the given constraints. First, the function count quadruplets is defined, taking nums as the input list. The variable n is initialized to store the length of the input list, and count is initialized to 0, which will keep track of the valid quadruplets. The solution employs 4 nested loops to iterate through all possible combinations of indices A, B, C, and D. The outermost loop starts with a from index 0 to n3, ensuring that there is room for 3 more indices. The second loop iterates B from A plus 1 to n2, the third loop iterates C from B plus 1 to n1, and the innermost loop iterates D from C plus 1 to n. For each combination of indices, A, B, C, D, the condition nums, A, plus nums, B, plus nums, C, equals nums, D, is checked. If the condition is true, the count variable is incremented by 1. Finally, after checking all possible quadruplets, the function returns the total count of valid quadruplets. This brute force approach works correctly but has a time complexity of O, n to the power of 4, making it suitable only for small input sizes. This implementation ensures clarity and correctness, systematically covering all possible quadruplets while adhering to the problem constraints. This is the Java implementation of LeetCode problem number 1995, count special quadruplets. The logic mirrors the provided Python implementation, using nested loops to iterate through all possible combinations of indices a, b, c, and d, and checking if the condition nums a plus nums b plus nums c equals nums d holds true. Java-specific differences include the use of explicit type declarations and a class structure. The solution has a time complexity of n to the power of 4, which is acceptable for the problem's constraints. Here, we start with the input array nums equals 1, 2, 3, 6. The length of the array is 4, and we initialize a variable count to 0 to keep track of the number of valid quadruplets found. Next, we iterate through all possible combinations of 4 indices to check if the sum of 3 numbers equals the fourth number. First, we fix nums a at index 0 with the value 1. Then, we fix nums b at index 1 with the value 2. Moving further, we fix nums c at index 2 with the value 3, and finally, we fix nums d at index 3 with the value 6. Now, we check the condition: does nums a plus nums b plus nums c equals nums d? Substituting the values, we have 1 plus 2 plus 3 equals 6, which is true. Since the condition is satisfied, we increment count by 1. After this combination, there are no more quadruplets to check, so we return the final count, which is 1. In this example, we have the input array nums equals 1, 1, 1, 3, 5, with a length of 5. Again, we initialize count to 0. Starting with the outermost loop, we fix nums a at index 0 with the value 1. Next, we fix nums b at index 1 with the value 1, and then nums c at index 2, also with the value 1. Now, we fix nums d at index 3 with the value 3. Checking the condition, we calculate 1 plus 1 plus 1 equals 3, which is true, so we increment count to 1. Continuing, we fix nums d at index 4 with the value 5, but 1 plus 1 plus 1 equals 5 is false, so count remains unchanged. After exploring all combinations where nums a equals 1, we repeat this process with other indices for a, b, c, and d. However, no additional quadruplets satisfy the condition. Thus, the total count remains 1. After iterating through all possible quadruplets in the array nums equals 1, 1, 1, 3, 5, we find that there is only one valid quadruplet. Therefore, the total number of quadruplets found is 1, and we return count equals 1. Now, moving on to the next example, we are given the array nums equals 3, 3, 6, 4, 5. The length of the array is 5, and, as always, we initialize count to 0 to track the number of valid quadruplets. Here, we start iterating through all possible quadruplets in the array nums equals 3, 3, 6, 4, 5. First, we fix nums a at index 0 with the value 3, and then fix nums b at index 1, also with the value 3. Fixing nums c at index 2 with the value 6, we now check two possible values for nums d. Fixing nums d at index 3 with the value 4, the condition 3 plus 6 equals 4 is false. Fixing nums d at index 4 with the value 5, the condition 3 plus 6 equals 5 is also false. We continue this process with other combinations of indices a, b, c, and d, but none of them satisfy the condition. After exhausting all possibilities, we find no valid quadruplets in the array. Thus, the total count remains 0, and we return count equals 0. In this problem, we are iterating through all possible combinations of quadruplets in the array nums, where the indices satisfy the condition a less than b less than c less than d. To analyze the time complexity, let's break it down loop by loop. The outermost loop runs from a equals 0 to n4, so it performs approximately in 3 iterations. For each value of a, the second loop runs from b equals a plus 1 to n3, which averages around n3/2 iterations. Next, the third loop iterates from c equals b plus 1 to n2, averaging n2/3 iterations per combination of a and b. Finally, the innermost loop runs from d equals c plus 1 to n1, averaging n1/4 iterations for each combination of a, b, and c. When you multiply the number of iterations across all 4 loops, the total can be expressed as a summation capturing all valid quadruplets. This simplifies to the binomial coefficient c, n4, which equals n asterisk, n1 asterisk, n2 asterisk, n3/24. This brings us to the conclusion that the time complexity of the algorithm is O, n to the power of 4, as the dominant term in the binomial expansion comes from the n-4 factor. Now, let's look at the space complexity. The algorithm only uses a few integer variables, such as count, a, b, c, and d, to track the indices and the count of valid quadruplets. It does not require any additional data structures or memory allocations, so the space complexity is O(1) or constant. Comparing this brute force approach with potential optimizations, we can see that while this method evaluates all possible quadruplets in O, n to the power of 4, time, there are ways to improve its efficiency. For instance, a more optimized approach might involve pre-computing sums of pairs and using hash tables to check against nums, d. This could reduce the time complexity to O, n^3, by eliminating one of the nested loops. However, such optimizations would introduce some additional space requirements. Lastly, regardless of the input size or content, the brute force approach always evaluates all combinations, making the best, average, and worst case time complexities uniformly O, n to the power of 4. To solidify our understanding of the time complexity, recall that the total number of quadruplets is derived from the binomial coefficient c, n4. The dominant term in this expression is proportional to n-4, since lower order terms and constants are negligible in big O notation. As a result, the time complexity is confirmed to be O, n to the power of 4. On the other hand, the space complexity remains O(1), because no auxiliary data structures are required, and the memory usage is independent of the input size. These characteristics of the algorithm highlight its brute force nature, where the primary focus is on correctness rather than efficiency. While optimizations can be applied, this approach provides a clear baseline for understanding the problem and its computational limits. When solving this problem, it's important to be aware of common mistakes that can lead to incorrect results or inefficiencies. One frequent issue is not handling duplicate quadruplets correctly. For example, if the input array is 1, 1, 2, 2, and the target is 6, the quadruplet 1, 1, 2, 2 might be counted multiple times. To avoid this, sorting the array and skipping over duplicate values during iteration using a condition like if nums I equals nums I1 continue can ensure that duplicates are eliminated. Another challenge comes from using an inefficient brute force approach, which involves trying all possible O, n to the power of 4, combinations of quadruplets. While this approach is straightforward, it becomes impractical for larger inputs. Instead, optimizing with sorting and the two-pointer technique reduces the complexity to O, n^3, which is significantly faster. Finally, mismanaging the order of indices, such as failing to ensure A less than B less than C less than D, can result in invalid quadruplets. Carefully structuring loops or pointers to enforce this order is critical for correctness. Another source of error is the incorrect use of hash maps. While hash maps can speed up lookups, mistakes such as allowing overlapping indices in pairs can lead to invalid quadruplets. A well-designed hash-based approach must account for these index constraints to ensure correctness. Additionally, ignoring edge cases can lead to failures in corner scenarios. For instance, you might encounter arrays with fewer than 4 elements, empty arrays, or extreme target values. These situations can easily be overlooked, so it's essential to explicitly check for them. For example, if the length of the array is less than 4, you can immediately return an empty list since no quadruplets are possible. Testing for these edge cases ensures that your solution is robust and handles all inputs gracefully. This problem is a great test of your ability to recognize patterns and adapt solutions. It builds on foundational problems like two-sum and three-sum, which involve finding pairs or triplets that meet a target condition. Interviewers often use this problem to assess your skill in extending these simpler solutions to more complex variations. Start by demonstrating an understanding of the brute force approach, but quickly discuss optimized methods, such as sorting and the two-pointer strategy, to show your ability to improve efficiency. Be prepared to explain the trade-offs between time complexity, like O, n^3, versus O, n to the power of 4, and space complexity, especially when using hash maps. Additionally, clear communication is key. Articulate how you handle duplicates, edge cases, and avoid redundant computations. Related problems like 2-sum, 3-sum, and variations like 4-sum 2 or the generalized k-sum problem can also provide valuable insights and help you draw connections to similar techniques. There are several alternative approaches to solving this problem, each with its own advantages and trade-offs. The two-pointer technique is a popular choice. By sorting the array and iterating with two nested loops for the first two numbers, you can use two pointers to find the remaining two numbers. This approach reduces the complexity to O(n cubed), which is much faster than brute force, though the initial sorting step adds an O(n log n) overhead. Another method involves using a hash map to store the sums of all pairs. This allows you to find pairs of pairs that match the target more efficiently, with a complexity of O(n squared), for building the hash table. However, managing index constraints and avoiding duplicates can be tricky in this approach. Finally, the recursive k-sum approach generalizes the problem for any number of elements, breaking it down recursively. While it's elegant and flexible, its performance is less efficient for specific values of k, such as k equals 4. Choosing the right approach depends on the context and constraints of the problem you're solving. Great job following along. To recap, we analyzed the brute force approach and discussed its limitations. Remember to practice using efficient data structures and algorithms for optimization. Thanks for watching, and don't forget to like and subscribe for more content. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!